Asha K, Assistant Professor, Sai Vidya Institute of Technology. The course that I'm going to teach in today's class is DSP, Algorithm and Architecture. So, in DSP, Algorithm and Architecture, you will be having the concepts called as linear time invariant system. In DSP, Architecture and Algorithm, this particular topic comes in module 1 for 17 scheme syllabus. So this particular DSP architecture algorithm concepts we are learning in today's class. The first one, linear time invariant system. The prerequisite for this particular DSP algorithm and architecture is that you have learned the courses called as signals and system and as well as DSP in the previous semester. So in this linear time invariant system, uh, there is a necessary for us to represent the system in terms of input output relationship for the discrete system. In systems, signals will be having continuous time signal, discrete signals. Similarly, we are representing here the input output relationship of a discrete system. So, the system to which the superposition theorem satisfies is called as a linear system. So, a system is one which satisfies the superposition principle. That particular uh, system is called as the linear system. When we are calling it as a linear time invariant system, it will have the inputs and it is also having the output. The input are represented here. These are called as x of n and the output are represented as with an alphabet y of n. If the system that is described by the same input or output relationship at all time, there is no change in uh, the input and output. So if they are representing all time the input output relationship, then we call it as time invariant. A system that is both linear in nature as well as not dependent on the time, that is time invariant, is called as the linear time invariant system. This particular diagram is the representation of representation of linear time invariant system. A time domain representation of LTI system is done using linear constant coefficient difference equation. So how we represent the system? We represent this system by using difference equation. So by considering difference equation or by choosing difference equation, I can represent the linear time invariant system. A unit sample or impulse response is used to characterize the LTI system. Say I'll have certain impulse response that is represented with h of n, suitably producing the output that is y of n. So in this LTI system, we basically use two main concept. The two main concept that we are using here is the first one is called as convolution and the second one is known as system function or the transfer function of the system. The transfer function and the convolution are the two concepts that we are using in case of linear time invariant system. Convolution is used to determine the response of the LTI system in time domain. The system transfer function is used to determine the response of the LTI system in case of frequency domain. So, we'll discuss these convolution and transfer function in detail in the next slides. The first one that I'm going to discuss here is convolution. So, in the previous semester classes, you have already learned the convolution equation. The convolution is nothing but an operation that relates the input or output of an LTI system to its unit sample response. It is mathematically represented as y of n is equal to summation k is equal to minus infinity to infinity x of k into h of n minus k. This can also be written as k is equal to minus infinity to infinity of h of k into x of n minus k. We can write this equation as x of n convolution symbol with your h of n, or your h of n convolution symbol with x of n. In the equation, the mathematical equation that we have written here, we have x of n is called as the input of the system and y of n is called as the output of the system, and we have h of n is unit sample or impulse response of the system. Unit sample or unit impulse response of the system. Unit sample, or it is also called as the impulse response of the system that we are having. Here the symbol, this particular symbol that we are having, right? This is the symbol that is used to represent the convolution operation. You can also call it as a convolution operator. This is used to represent the convolution operation. The above equation is used to compute the time domain response of a system to an arbitrary input sequence. So this gives us the time domain response. Time domain response will be obtained with the help of convolution. Moving on to this next topic, that is Z transform. In signals and system classes and as well as in the digital signal processing concept, we have learnt Z transform equations, and in detail we have learnt and complete one module of this particular topic. Here the Z transform is used here. So the frequency response associated with the endpoint sequence x of n is given by the frequency response associated with the frequency response associated with endpoint sequence. Say I have here an endpoint finite sequence, x of n. For this finite sequence, endpoint sequence x of n, the frequency response x of e per j theta is equal to summation n0 to capital N minus 1 into x of n into e per minus j n theta. So here if I replace this, e per j theta is equal to z. Now just observe x of z in z domain is equal to 0 to n minus 1 into x of n into z to the power minus n, where this x of z is called as the z transform of x of n. The parameter z is related to digital frequency theta. So this is related to digital frequency theta, where theta is called as the digital frequency. So that this x of z represents the frequency response in terms of z. So x of z is going to use to represent the frequency response, frequency response in terms of z. So this is the one more topic that we have in this particular class. Moving on to the system function or the system transfer function. The system transfer function, or it is also called as system function, it is defined as the ratio of z transform of the output y of n to that of input x of n. So we know that h of n is equal to impulse response of the system, output response of the system to the input response to the system. So if I apply here the z transform system function, h of z is equal to capital Y of z to the capital X of z. Here h of z is called as the transfer function of the LTI system, or it is also called as the system function, or it is also called as the transfer function transfer function of the linear time invariant system. The system function here, it characterizes the system in the frequency domain. It is used to characterize system function in time domain. System function in time domain. H of z here is a complex function of is a complex function of z. So this consists of the location of poles and zeros of the z domain. So here if we are having, it is used to characterize the transfer function. Poles are the roots of the denominator and zeros are the roots of the numerator. So here poles are the roots of the denominator and zeros are the roots of the numerator. So the poles are here, the poles are represented by the, so this is your numerator and this is your denominator. Here poles are the roots of the denominator and zeros are the roots of the numerator. So the location of the poles and zeros leads us to one to determine the frequency response of the system. So the system function h of z, it is the ratio of the z transform of the y of n to the z transform of the x of n. So here we have to concentrate on poles and zeros. The poles and zeros are used to characterize the LTI system, where this poles and zeros will be present. So these poles and zeros LTI system. So for this LTI system, for this LP linear time invariant system, for this LTI system, the poles are nothing but poles poles are nothing but the roots of the denominator, roots of the denominator, roots of the denominator, and here zeros will be present. Zeros are nothing but the roots of the numerator, roots of the numerator. So after this topic, that is convolution, Z transform, and system transfer function, we are moving on to the next topic called as digital filters. So what are digital filters and how these digital filters are represented, that we are going to learn here. So a filter is nothing but a sequence H of n that operates on the input sequence x of n to generate the output sequence x of n to remove unwanted component in the uh, disturbance or not necessary component in the electronic system. We use this kinds of filter. So here in the terms of representing this particular digital filter is a generally a sequence h of n that operates on an input sequence that operates on an input sequence x of n. So to obtain the output to obtain the output y of n. Here the sequence is consisting of filter coefficients. So the input x coefficients are called as bk and the output y coefficients are called as ak. So the input x coefficients are represented by this, the output y coefficients are represented with this. The general equation that you have studied in the previous classes, that is y of n is equal to summation k is equal to 1 to capital N into ak y of n minus k plus summation k is equal to 0 to capital L into b suffix k into x of n minus k. This is the general equation which is used to represent the filter. This is filter equation. So this particular filter equation can be represented in uh, block diagram representation or block diagram representation of the digital filter. The block diagram representation of this equation or this particular filter equation will have the delays, adders, and the input and output. So consider the input x of n. This is delayed by 1 unit z to the power minus n and multiplied with a parameter, that is coefficient. First one is b0. The second one, after delaying with 1 unit time, I'll be having uh, b1 added by using an adder. So this b1 and b0 are multiplied by using multiplier. Again, one more delay unit is used here, second delay unit. Then after this, I'll multiply this with the second coefficient, that is zeroth coefficient, first coefficient, and b2, and again this will be added here. So it goes on. The last value that we have in this particular equation is with respect to x is capital L. So we'll consider here. So we'll write here the last z to the power minus 1 is the delay that we are having. Then multiplied with the factor BL. Then this is connected to the adder which is above here. So if I write the delay here, x of n minus 1, this is x of n minus 2. So when it comes to here, this is x of n minus L, and here it is x of n minus of L minus 1. So this is written as x of n minus L plus 1. So now if here the multiplication factor here is BL minus 1. So again this will be added to this adder. Coming to this particular end, I'll be having again one more adder. I'll be connected this to the output y of n. Consider output y of n delayed by 1 unit. So what I am going to get? The first one, that is y of n minus 1 delayed by 1 unit, y of n minus 1. Similarly, if you put one more delay unit here, z to the power minus 1, we'll be getting y of n minus 2. Again, put here one more adder and all those things will be added. So always the first one will be here 1. So next when it comes to this side, here we'll be having the factor, that is a1. Next we'll be having here a2. So this goes on. So when it comes to the last side, the maximum value of y here is capital N. So when we have capital N here, so one more delay unit, the last delay unit that I'll be having here is z to the power minus 1, that produces y of n small n minus capital N, and at that particular end, so this is multiplied with a capital N and added to the adder. So this is added here, multiplied here, and it is added here. Above this, we'll be having cap small a capital N minus 1, suffix capital N minus 1, and the delay that we will be having here is y of minus of n minus 1. So if I simplify here, y of n minus of plus 1 is the simplification. So after this particular representation of block diagram of the filter equation, so this is the above structure that employs the feedback, and as well as the current output depends on the past outputs in addition to the current and past inputs. So here by choosing proper coefficients sequences, the coefficients are at the output side, y of n side, we have one a1, a2, an minus 1 up to an, and we'll be having here at the input side b0, b1, b2, bl minus 1, bl. So we can design the filters such as low pass, high pass, band pass, and band stop. So this designing of the filter involves determining the coefficients to obtain the desired frequency response. So after this particular topic, we'll move on to the important topic, the modification of this particular filter equation. The modification of this particular filter equation, in this, first we'll assume that all the output delayed versions are zeros. Okay, first we will learn the concept called as finite impulse response filter. In case of finite impulse response filter, the general filter difference equation is given by y of n is equal to summation k is equal to 0 to capital L into bk into x of n minus k. This equation defines the finite impulse response of the filter, the unit sample response of the FIR filter. It lasts for finite time dependent on the number of filter coefficients represented by only b of k. So we'll not be having any a suffix k coefficients here. The frequency response of the particular filter. The frequency response of this particular filter, the frequency response is given by the frequency response is given by, I'll write here, y of n by your x of n, that is equal to h of n, that is equal to summation k is equal to 0 to L into bk into delta of n minus k. So if we write here the frequency response h of e power j theta, that is equal to summation k is equal to 0 to L into bk into e to the power minus j k theta. So this equation, in this particular equation, so for this delta of n minus k, so we are writing e power minus j k theta. H of n, that is h of j e power j theta. So k is equal to 0 to L into bk into e power minus j k theta. Now, in terms of Z transform, in terms of Z transform, h of z is equal to summation k is equal to 0 to L into k is equal to 0 to L into bk into z to the power minus k. Since FIR filters has no feedback, so here there is no feedback in case of FIR filters from the output side. So there is no feedback in its structure. It is always a stable filter. So this is called as the stable filter. So it is known as the stable filter. So it is a stable filter. Symmetric coefficient FIR filter provides linear phase constant group delay. So group delay calculation is possible in case of FIR filters. This property makes this FIR filter suitable for applications that cannot tolerate the phase distortion. So this is the one of the property. So we can easily calculate the group delay in case of FIR filter. So this property makes the filter suitable for the application that will not tolerate the phase distortion. So phase distortion tolerance negligible wherever it is negligible. So in such cases, so this particular type of filter is used. So what are the major disadvantages of this FIR filters, finite impulse response filter? To obtain the desired frequency response, the number of coefficients that is required here is large. The coefficients required are large. So this is one of the disadvantage. Since the coefficients are large, since the coefficients required are large, so computation time required will be more. The computation time required is more. The computation time required for this is more. So we will take up the example of FIR filter, finite impulse response filter. So this is represented by a difference equation. The particular difference equation filter, an FIR filter, finite impulse response filter. For this particular finite impulse response filter, we will consider the difference equation. So for this FIR filter, the example of FIR filter that we are using here is y of n is equal to 0.5 x of n plus 0.5 x of n minus 1. This is the equation that describes the finite impulse response filter, where x is the input sequence, y is the output sequence, and x of n minus 1 is the delayed version of x, or nothing but the past values of the x. So if we further simplify here, y of n is equal to 0.5 times of x of n plus 0.5 times of x of n minus 1. So next step what we are doing here is we are writing the z transform of this by considering z transform on both the sides. 0.5 times of x of z plus 0.5 times of z to the power minus 1 into x of z. Now if we take x of z outside common, and if we take this to the denominator, I'll be having 0.5 plus 0.5 to the power z to the power minus 1. So this is h of z. The h of z, the equation of h of z, 0.5 plus 0.5 into z to the power minus 1. So in this equation, if we replace z by e power j theta, so what happens? H of e power j theta is equal to 0.5 plus 0.5 into e power minus j theta. So e power minus j theta. So this is the h of e power j theta is equal to 0.5 plus 0.5 into e power minus j theta. So now what we are going to do here is, so we'll further elaborate this equation and we'll try to find out the magnitude response and the phase response. So what is this h of e power j theta? This h of e power j theta is the frequency response of the LTI system. So for this FIR filter, so for this FIR filter, the frequency response is given by h of e power j theta, that is equal to 0.5 plus 0.5 into e power j theta. So now what I'll do, I'll write the further equation. H of e power j theta is equal to 0.5. I'll consider that there is a 1 here. Next 0.5 into e power minus j theta. For further simplification, what I'll write here is, I'll write here 1 is equal to e power minus j theta by 2 into e power j theta by 2. Further, I'll expand this e power minus j theta as e power minus j theta by 2 into e power minus j theta by 2. So after writing this 1 is equal to this value and e power j theta is equal to this value, we'll substitute in this particular equation. After substituting, h of e power j theta, that is equal to 0.5 into e power minus j theta by 2 into e power plus j theta by 2 plus 0.5 into e power minus j theta by 2 into e power minus j theta by 2. So now we'll take the common 0.5 and we'll take this e power j theta by 2 as common outside. We'll be left with e power j theta by 2 plus e power minus j theta by 2. Moving on to e power minus j theta by 2, 0.5 can be written as 1 divided by 2. E power j theta by 2 plus e power minus j theta by 2. This 1 divided by 2 is written like this. Now, e power minus j theta by 2 into cos theta by 2. According to the trigonometric relationship, cos x in terms of exponential is e power jx minus e power jx divided by 2. So by using this particular relationship, trigonometric relationship, we are going to write e power j theta by 2 plus e power minus j theta by 2 divided by 2 as cos theta by 2. So this is nothing but the frequency response h of e power j theta. After having this particular equation, h of e power j theta is equal to e power minus j theta by 2 into cos of theta by 2, we will write down the magnitude response and the phase response. In the MATLAB, we use the commands called as absolute and angle to calculate the magnitude and phase response. Here we have the magnitude response is given by the magnitude response. The magnitude response is given by magnitude of h of e power j theta, that is equal to m of theta, only the absolute terms. So we have here cos theta by 2 is the absolute values that I am going to get for different values of theta in radians. This is m of theta, magnitude response. Moving on to the phase response. The phase response of h of e power j theta is written as h of e power j theta, that is equal to phase of theta, that is equal to minus theta by 2, that is the first term value, and also the angle of cos of theta by 2. So whatever the different angles of cos of theta by 2 for theta in radians, so we are going to add these two things and we are going to obtain the phase response. In MATLAB, we use the commands used for magnitude responses, ABS, that is absolute values, whereas to calculate the phase we use the command called as angle, ANGLE. For this particular equation, the FIR filter equation that we have considered here is, the FIR filter equation that we have considered here is y of n is equal to x of n plus 0.5 x of n. I'll just alter the sentence. The equation that we have considered here is 0.5 x of n plus 0.5 x of n minus 1. The magnitude response obtained is cos theta by 2 and the phase response is obtained is, so this is the phase response value that we have obtained. So after obtaining this phase response and the magnitude response, the group delay, which represents the delay to various signal frequencies, can be obtained by differentiating and neglecting the phase response function. That in detail, the calculation that we are not discussing here, we are directly writing for this particular example. For this particular example, here the group delay for this particular case is given by group delay is equal to 1 divided by 2. So the block diagram representation of FIR filter. So we have to represent how to draw the block diagram for this particular difference equation. So for this particular difference equation, there is no delay. So what we have first, input we have, that is x of n. This input is multiplied by, it is multiplied by a multiplication factor, that is 0.5, and again this is delayed by 1 unit, z to the power minus 1. This is also called as unit delay. It is also known as unit delay, and after having this unit delay, the output here is x of n minus 1. Again this is multiplied with a factor 0.5, that is nothing but the coefficient b0 and b1. These two are multiplied here and again this is added. So we'll be having here the addition of this equation. I'll just write here. The addition that we are having here is an adder circuit. An adder symbol is used here. And finally, we are going to obtain the output y of n. This is called as the block diagram of finite impulse response filter. So block diagram of finite impulse response filter is completed. Moving on to the phase response and the magnitude response. The phase response and the magnitude response is obtained by using those equations, that is m of theta and p of theta. For this, the phase and magnitude response, if you go on substituting the value of theta in radians, the value of theta that we are measuring here is in radians. So for this first one, we wanted to plot the magnitude response. The second plot that we are going to represent the phase response. Magnitude response and phase response is important here. For this magnitude response and phase response, we'll note down the x-axis values 0, 1, 2, 3, 4, 4.5. It goes like this. Coming to here, it is in radian 0, 1, 2, 3, 4, and again we'll be having till here, like if it is say 5, we will write here till it is 5. So above in this particular the y-axis will be from 0 to 1. So in between I may have 0.5 also here. So here it starts with 0, the phase response. After starting with 0, so we'll be having here it as minus 0.5, minus 1, minus 1.5, minus 2. And after plotting this x-axis and y-axis for the magnitude and the phase spectrum with the help of this equation, one is cos theta by 2 and the other one is minus of theta by 2 and plus an angle of cos theta by 2. If we plot the graph will look like this. First value of magnitude spectrum cos 0 is 1. It starts with 1. And afterwards, for different values of theta in radians, I'm going to get a curve like this. So this is the magnitude response curve that we are going to obtain. Similarly, if we substitute uh, the phase different phase values, that is theta in radians minus theta by 2 plus angle of cos theta by 2, we are going to obtain the phase spectrum. The phase spectrum will be like this. So this is the magnitude response and phase response for finite impulse response filter. The difference equation that is represented here is y of n is equal to 0.5 into x of n plus 0.5 into x of n minus 1. This is the difference equation that we have used for finite impulse response filter. So we'll end here. We'll take up the next topic in the next class. Thank you.